Is going to be chapter 27. I will go over the lecture first, and then I will go over the problem solving. Here you have to pay attention to so many points, these two chapters. Now first we're gonna introduce magnets, and we're gonna talk about that magnetism is a natural phenomena, and actually we can find magnets in nature, and there are many creatures that they use internal systems that they are really working based on magnetism. We're gonna learn also how magnets interact with each other. One of the most important things in this chapter is we are going to talk about magnetic forces and how they are really affecting moving charges and also electric currents. Then we will talk about these two things, and these are really super important. How magnetic field lines are different from electric field lines. What is really the difference between electricity and magnetism, and some practical applications of magnetic fields in chemistry and physics, including electric motors. And also we are going to talk about current loops when they are really placed in magnetic fields. Now, as I said, like magnetism, maybe this is one of the first things that you're gonna learn in science when we are going to talk about these permanent magnets that you have them in the classroom. Maybe I would say first year of science class. And we're going to find that some of the materials are really able to attract unmagnetized iron objects, and also some of the materials can be actually attracted, and some of them they are not. And we know that there are magnets that they're going to attract or repel each other. Also, maybe we use compasses for finding directions, and this is an interaction between the compass itself and the magnetic field of the earth. Now, how I will say magnetism is created. We're gonna maybe talk more about it also in chapter 28, because we are going to try to calculate magnetic fields for different situations. But also we need to know that the interaction or the force can only act on a moving electric charge. It's kind of like if the charge is not moving, we will not have any forces. How can magnetic forces, which act only on moving charges, explain the behavior of a compass needle? And we will talk about this in a little bit. Here, of course, maybe you could recognize that if you have two magnets and you put them, side to side, they might attract each other. And if you reverse, you are going to get maybe repulsion. Here we are just displaying bar-shaped permanent magnets. And we will see that when we have the south is facing the north, they're going to attract each other. And when we have them, this is north or south. When we have north with north, we're going to have, repulsion. I will say here, then we can conclude here that opposite poles attract each other and like poles repel each other. as was shown in here. Now let's see here if we will, go over more details. Magnetism is actually related to some of the materials. It's not related to, all the materials. Not every metal, I will say, is gonna be can be a magnet, and not every metal can be attracted to to a magnet. All right, let's talk about things that they are really important. And the first thing I'm gonna start with is magnetism and certain metals. An object that contains iron, but it is not itself magnetized, it shows no tendency to point north or south, is attracted by either pole of a permanent magnet. Then if we have something that is not magnetized, it's not a magnet, then it can be attracted from both poles. Magnetic field of the earth. The earth itself, it is a big or a huge magnet, and its north geographic pole is close to a magnetic south pole, which is why the north pole of a compass needle points north. Then I will say, if this is really I will say this is the earth. Okay, this is the earth, and this is, let's say, the north geographic, and this is the south. We're gonna find that the magnet inside the earth, it is opposite, SN. And therefore, if you have a compass, is gonna point towards the North Pole, because its north is gonna be attracted to the south of the earth, and its north is gonna be attracted. Its north is gonna be attracted to the south of the earth, and its south is gonna be attracted to the north of the earth. The Earth magnetic axis is not quite parallel to its geographic axis, which is the axis of rotation. So a compass reading deviates a little bit from geographic north. This deviation, which varies with location, is called magnetic declination or magnetic variation. The magnetic field is not horizontal at most points on the surface of the earth, and it has what is called inclination. Now, magnetic poles always come in pairs. We cannot have mono poles, like we cannot have a single pole. And this is the main difference between electricity and magnetism, or between electric things and particles and magnetic things. That is, we cannot separate first, we cannot separate north from south. Even if you have a magnet and you're gonna cut it into two pieces, it's gonna be north and south, and then you keep on cutting, it's gonna stay having a north and south pole. Whereas if we have electricity, of course, we can have a single negative charge or a single positive charge. Now also, we need to know that a compass near a wire with no current points north, because it will be affected by the magnetic field of the earth. But if we will get a current going through this conductor, then I will say the compass needle reflects somewhat in a direction, and this is now because it is affected by two magnetic fields. Now, I will say, of course, and as I said, we're going to study this next chapter, is that if I have a moving charge or if I have a current, then I will be able to get a magnetic field in the surrounding space. How we going to calculate that? We are going to do this in chapter 28. But also, we need to know that if we have a charge that is moving or we have a current, then the magnetic force is going to be exert, forces on this wire or this charge. Then if we have a charge that is moving in a magnetic field, or we have a conductor that having current and it's in a magnetic field, then we're going to have a magnetic force. Like an electric field, a magnetic field is a vector field that is a vector quantity associated with each point in the space, and we will use for it B for magnetic field, and it's going to be uppercase B with that arrow. And at any position, the direction of B is defined as the direction which the north pole of a compass needle tends to point. And that is really a convention that we are going to use. Now, the magnetic force on a moving charge, we here, as I said, if we have a charge that is, in a magnetic field, then the magnitude of the magnetic force on it is going to be proportional to the component of the particle's velocity, which is perpendicular to the field. If the particle is at rest or moving parallel to the field, it experiences zero magnetic force. Now, remember here we have the force is going to be a vector quantity, therefore it has a direction and it has a magnitude. Now, I will say, in general, the force is going to be Q, which is the charge, the particle's charge, times V, which is the vector, the velocity, times B, and that is a cross product. I provided you in the main page for chapter 27. You have 2 videos about using the right-hand rule, and I will explain it, of course. And these right-hand rules, we are using them to determine the direction of the force. Now here, if we have, this is the green is the velocity, and the blue here is the magnetic field. They are in the same plane. Then the force is going to be perpendicular to the magnetic field, and the velocity, the plane that is connecting both. And here I will say, whenever we're going to have B and V, they have 90 degrees between them, this is going to be the maximum force. Now, why is that? Because remember, for a cross product, if you want to calculate its magnitude, not including direction, is going to be Q V B sine theta. And theta, it is the angle between V and B vectors. And when it is 90, is going to be 1. Therefore, the maximum occurs at 90 degrees. And of course, as theta is changing from 90, this is going to cause the force to decrease. Here, showing you that also, like a charge moving at an angle phi to a magnetic field experiences a magnetic force with magnitude that is going to be Q. We don't have the charge, I would say, we're going to have it like just the absolute value of the charge, VB sine phi. I like always to use theta, and the force always, it is perpendicular to the plane containing V and B. But the magnitude, of course, is going to be less if we have an angle that is really less than 90. Here, I'm just showing you what is really the way of calculating or finding the direction of the magnetic force on a moving charged particle. I provided you with two methods. This is the method that we are using in the textbook, which is the right-hand rule for, in general, I will say any two quantities that they gonna have a cross product. You're going to place V as a vector and B as they are really tail to tail. Then here, if you look here, this is B, okay, and this is V. They are, their tail is here. Now we are going to make V go to B. Why V go to B? Because F, it is Q V cross B. Then V is gonna go to B, and then you're gonna use your right hand. You're gonna curl your fingers in the direction from V to B, and your thumb is gonna show the direction for the force. Okay. Now, then imagine turning V toward B in the VB plane through the smaller angle, and then the force acts along line perpendicular to the VB plane. Curl the fingers to your right hand around the line, and then your thumb now points in the direction of the force. There is another method, and it was explained in a video, where you are going to use the thumb for your velocity, and you're going to use the fingers, the four fingers, in the direction of the magnetic field. Then a vector from your palm, from your hand palm, is going to show the direction of the velocity. This is most common, I will say, for the magnetic force, but I will say, I like the method that we are using in our textbook as well. Yeah, this is a very important, idea, because we're gonna do it again also. We're gonna use it so many times, and this is gonna make you able to calculate the vectors whenever you are, working with this topic. Now, the right-hand rule gives the direction of the force on a positive charge. Then if you have an electron, you are going to assume that your charge is positive. You are going to determine the direction, and then it's going to give you that the force is going to be along the positive x-axis. Then you're going to say, because I have an electron, is going to be in the opposite. Okay, here the next slide shows the 3 steps involved in applying the right-hand rule, which I was talking to you about. Place the velocity and magnetic field vectors tail to tail. Imagine turning V toward B in the plane through the smaller angle, and then the force acts along a perpendicular line to the VB plane, and you're gonna curl your fingers in that direction, and then your thumb is gonna point in the direction of the force. This is the what I was explaining to you, and these are really the same idea. Now, if we have like equal velocities but opposite signs, which means let's say an electron and a proton. Electron and a proton, this is a needed information for you. You need to know that they are both having equal charges but opposite. If we have two charges, they have the same magnitude but opposite sign, moving in the same velocity, with the same velocity in the same magnetic field, then the magnetic forces when the charges are equal in magnitude but opposite in direction. And that is really because, again, as I said, for the charge that is negative, you're gonna assume that your charge is positive, and then you're gonna determine what is the direction for the F, and then you're gonna say is gonna be in the opposite direction. The cathode ray tube, this is the CRT, this is one of the most important applications where we have an electron beam in the cathode ray tube. Like the electrons, they will be generated, there will be a beam, and such as that in an, the TVs or in oscilloscopes, and like many devices. If there is no force to deflect the beam, it strikes the center of the screen, but the magnetic force deflects the beam and create an image on a phosphorus screen that is going to be, when the electrons they're going to hit, they're going to create light. I'm going to stop here and continue later.